In this presentation, I will go over the history of AFGROW and then discuss some of the new features that are included in version 5.2.3. In 1985, AFGROW was developed by Mr. Ed Davidson at the Aeronautical Systems Division of the U.S. Air Force, and I modified the code to use tabular crack growth rate data using my T method and renamed the code ModGrow. Then in 1987, ModGrow version 1.0 was developed at the U.S. Air Force Wright Aeronautical Laboratory. In 1989, version 2 was created in Turbo Pascal and was the first time it included real-time plotting. In 1994, AFGROW version 3 was developed for the Unix workstation, and it was the first version to have a really friendly user interface. And in 1996, AFGROW version 3.5 was created in Microsoft Windows, and it also had a user interface that was very nice, but we found that the Unix workstations were not the future, and we switched everything at that point was switched back to Windows. Also, one of the big features that was added was the Microsoft COM automation that allowed other Windows programs to communicate with AFGROW. In this example, one of the most widely used features was the ability to communicate with Excel and set up multiple runs in advance. In 2000, version 4 came out. It was the first version that included our advanced interface. It was multiple cracks, multiple holes, with the drag and drop jump pad with the specimen properties that you could change. Then another big feature that came about that same time was the ability to communicate with external case solvers, such as in this case stress check. So AFGROW would then set up the parameters, pass them to stress check. Stress check would calculate the Ks for one or more cracks, send the information back to AFGROW. AFGROW would increment the crack, and then the code would then repeat. In 2010, the first commercial version, version 5, was taken over by LexTech. It included continuing damage, where we had a crack on either side of a hole. One crack would grow to the edge, the geometry would change to a slot, and then the crack growth would continue on the other side of the hole. We also included spectrum and stress intensity filtering, which allowed users to modify either the spectrum or the beta factors as a function of crack length. In 2014, version 5.2 was released. It was a big change because now we had updated the entire graphical user interface, and we included the stress intensity factors for countersunk holes. Also, we included warnings when certain solution limits were violated. Now version 5.2.3 demonstration follows. You can see one of the things we have here, we have tabbed windows. We have the ability to dock and undock. You can, as you see, pin and unpin or hide the views. You can move the windows any place you want. You see the docking locations shown here on the screen. And you can take a window and then you could move it to the side. You can move it to the tabs. As you see here, it comes in the tab, goes in the tab view. Again, we can see all the options for moving and docking windows. The classic models, as always, we have the dimensions and load tabs where things can be changed. And then here we have the notifications when anything goes outside the limits. That's also a tabbed view. And then advanced model, see here we can drag the countersunk hole just as we could drag the regular hole, straight shank holes. And there's an example of how you can change any of the parameters or properties for any object. Dragging the corner cracks to the countersunk hole. The current solution allows you to only place the crack at the fading surface. And there we see the output. Now, unlike with the countersunk hole, for the straight shank holes we can drag the hole any place on the plate and put two cracks, a crack on either side of the hole. And then change the properties. And run the prediction. In this case, the one corner crack went to the edge, became a through crack, and then the other crack continued as continuing damage with a notch. Okay, so to summarize, the new features, we have the classic wave function solutions for over 30 different crack geometries, in many cases axial bending and bearing loading. We have advanced multiple crack capability. We can look at 2 independent cracks in a plate, including the hole effects with up to 4 holes. We can do the non-symmetric corner cracked holes, and as I mentioned, the continuing damage solution for a crack that has grown to one edge. Finite element-based solutions are available for 2 non-symmetric corner cracks. These are available in table lookup for cracks at holes as well as cracks growing towards holes using the ability to superposition for the effect of adjacent holes. And we can look at cases with more than one crack growing from a row of fastener holes. Now, the advanced solution for non-symmetrical corner cracks was developed for a number of parameters. As you can see here, R over T going from 0.1 to 10, A over C from 0.1 to 10, and A over T from 0.1 to 0.99. Now the problem with this was that 0.1 wasn't small enough to get some of the smaller 005 flaws, for example, that many users would like. So we had to come up with another way to do this. The current database includes, as you see here, 1,890,625 different solutions in the database. And even with that, we only went down to A over T of 0.1. So because of the number of solutions, we really couldn't go back and try to fill in the blanks all the way back to close to 0. So what we did was we looked at extending the beta to the 0 crack length limit by using the correction for the free edge times the KT, whether it's for the axial case or the bearing case, times 2 over pi, which corrects for the part through crack. Now also, we have the ability to look at 11 points along the crack front. So you see here the points are spaced or weighted more towards the edges. The object here, if you use the multi-point option, is to allow us to better predict the shape of the crack. Now when we extended the solution back to what we call the limit as we go to 0, A over T, you can see the old solution was limited to A over T of 0.1 and we didn't extrapolate. The new solution here is a spline fit that shows what the new solution does compared to the old solution, which allows you to go back to essentially 0 crack length. Now another thing that changed in version 5.2.3 was the offset correction for bearing load. The solution simply takes a center crack solution, multiplies by an offset effect to give you the solution for the offset hole, whether the crack's going towards the near edge or whether it's going towards the far edge. Now, the solutions for the axial case and the bearing case are not the same. As you see here, the solid lines are the correction for the axial loading case, and the data points that we've obtained by finite element solution were the corrections required for the bearing load. Very different. As you see here too, what we had to do to make this closed form solution was to constrain one edge from bending in plane. If we didn't do that, it was almost impossible to obtain the closed form solution. But in real application, on an airframe, skins will be attached to stiffeners, and I think that the assumption that we have a constrained case is probably valid for most practical cases. In this case, we looked at edge distance, edge to diameter of 0.75, 1, 2, 4, 8, and 16. Crack length of project max from 0 to 0.95. And this parameter, W minus 2E, the edge distance over W, it gives you the idea of how much offset there is. So that, in the end, we looked at curve fits. Here's an example for E over D equal to, probably the most common. For the crack going towards the near edge, the points are the finite element solutions that we had, and the lines are the curve fits. For the far edge, you see we had less data. It was more difficult to run all the possible cases, but the curve fits were selected so that the functions the functions were well behaved. They don't go off wildly after you exceed the limits of the finite element solutions. Another thing that was done in the new version was expanding the tabular solution for a single through crack at a hole in a bearing load. The previous solution had solutions for W over D going from 1.3 to 1,000 for the plate, but between 4 and 8 there was enough change that when the interpolation was done there was significant error, so we added solutions for W over D of 5 and 6 to solve that issue. Now the countersunk hole solution was provided by Rainier Uric. This was his PhD thesis at Delft. We have solutions for bending, tension, and bearing. However, right now only the tension and bending are implemented because of some issues that we found with the reference stress for bearing, which will be worked out as soon as possible. For a single crack, we can have a single countersunk hole anywhere in the plate, but for a double crack it can only be symmetric at this time. These solutions are shown here. The range of solution goes R over T between 0.1 to 2.4. The B over T, or the as you see here, B is defined as the straight shank percentage of the thickness of 0.05, which would be the knife edge, 0.25 and 0.5. A over C goes between 0.5 and 5, and A over T varied. There were 5 values in the straight shank portion, 10 values in the countersunk area, up to C over R equal 5. In this case, there were 10,080 solutions in the database. Some of the issues that were involved here is that we have the corner crack at the fan surface. As the crack length in A dimension approaches the knuckle, then we have to transition to use a virtual A so that we can still maintain A over T going between 0 and 1. And then once we transition through the thickness, we have to keep track of 2 C lengths, one on the near surface of the fan surface and one on the far surface, which we call C2. Now, the spectrum generation tool is probably the biggest new feature that we're adding to this release, and it allows us to do a lot of new things and things that will be released in later versions of AFGROW as well. Here's a demonstration. Create a new spectrum. We give it a name. In this case, example. We give the subspectra a label. In this case, we'll call them flights. They don't have to be. They can be anything you'd like. Now we're going to add a subspectra. This will be flight number 1. We'll add a level. We'll create a maximum. In this case, it'll be normalized, and a minimum, and a number of cycles for a level. And at the time, you'll see that plotted at the bottom of the screen. We'll add another level, level 2. Give it a max and a min, number of cycles, and then you'll see, of course, you'll see it down below. Now, in addition to be able to type it in by hand, we can delete, we can cut and paste, and you'll see here how we'll be able to cut and paste. We'll add a level, go back to Excel. There's some data in an Excel spreadsheet, for example. Max, min, and cycles. We'll copy the block. And then we'll simply paste it. And there it is. And again, you see it below. Now we're going to add another subspectra, and that will be called Flight 2. Add levels. Again, we'll do one manual. Type it in. And now we'll go back to Excel. We'll grab another portion of that history. We'll copy it. I'm going to insert now. And now we insert that into Flight 2. So now we have two subspectra, Flight 1 and Flight 2. Now we'll check the sequence. We have, again, we create those two flights. We're going to use those flights now. We're going to build a spectrum. Now first we added Flight 2 and then a Flight 1. You can do that in any order you'd like. We added another Flight 1, another Flight 2. So you get the idea. You can take any of those, your subspectra. It checks to make sure that all of them were used. Everything you created was used in this spectrum. Add another Flight 2. And on, as much as you'd like. And down below you see the color change to denote each different subspectrum. And we can look at exceedance plots. We can look at R plots. We can look at what stress ratios are used in the spectrum. We can zoom into the view, just like you could in AFGROW's spectrum view. Fairly intuitive interface. We really would like feedback from users to see what we can change. You can see the version spectrum manager right now, and we also have damage tags. So we can create our own custom tags, damage tags. The damage tags will be used down the road when we have a post processor that will be able to track damage that was caused by any one of the levels in your spectrum. When you tag them, then it will sum up all the damage that has occurred. We also have the ability to include tags for things like temperature. So if you have a crack growth rate data at different temperatures, you can tag the spectrum. Each subspectrum can be tagged at a different temperature, and then the appropriate crack growth rate data can be used for that subspectrum. That ability will be coming out in a later release of AFGROW, but for right now, the ability is included in the spectrum manager. We can also truncate. We can truncate at a given level. That would be the delta between any max and min. We can then see the result after you do that. We can clip a spectrum. In that case, you get the upper bound. It's from 0.79 to 0.6. And you see on the lower screen that everything was truncated back to 0.6. Again, we look for user feedback on all these capabilities. We can also take a spectrum and convert it to multi-channel. In this case, we do 3 different channels. Initially, it just copies all 3 for axial, bending, and bearing, and then these can be changed. The only limitation is the cycles have to be the same. This feature we really would like feedback. I anticipate that this will be changed, but at least for now, it gives us the ability to look at all three components separately or independently. So now finally, we have the user notification system I mentioned earlier. Here's a close-up. It just tells you for the given model the condition that's valid, and then every time it has an output, it looks to see, it tells you that that was outside the range. Don't be concerned, for example, we see in this case, it was the valid range was 0.2 to 2. This case showed 2.02. If you see a deviation that is close to the limit, chances are there's not much to worry about. If you see a deviation that far exceeds the limit, then I would be more worried. Anyway, this was something that was desired by many users, and now it's finally included in AFGROW. So as far as future plans go, one of the things we'd like to do in the near future is to have a 64-bit version of AFGROW. We would like to have the ability to use different crack growth rate data as a function of spectrum and crack tips. So we can look at a crack growing through the thickness versus a crack growing along the width and changing the crack growth rate data. As I mentioned before, we will do this for temperature, and we'll tie that to the spectrum through the tagging. We'll look at the ability to have user-defined crack growth rate models for the same reason. We wanted to update our wave function solutions. We're still looking to verify what we have, the new solutions that we have. We're going to look at countersunk solutions for bearing. Bending is finally done, but bearing is not done. Advanced solutions for combinations of multiple corner and through cracks. We've been waiting for this for some time. We don't know when it's going to be available, but we hope it will be available in the next year or two. We wanted to look at using 2D user-defined beta for two interdependent through cracks that can be assigned different plate thickness values. This was useful for people that wanted to put in their own solution in two different directions and then account for thickness for each case separately. The multi-site damage model, where we have multiple cracks at multiple holes. At first, we'll do this for a very wide plate, and then we'll see where it goes from there. We also have been requested to look at the effective stiffeners in the panel. That comes out of Rook and Cartwright, and we'll hopefully put that in the near future as well. And the ability to communicate with an external material database also goes along with what we talked about earlier about using different crack growth rate data for different crack tips and temperatures. And as I also said, we're going to look at tracking damage as a function of spectrum loading, where we can tag a spectrum and then summarize the damage that had occurred for each tagged level. And finally, we'll have a undo redo capability.